It's time for another amazing chemistry video with Mr. Stapleton! Proudly sponsored by Farmer Junior Nice Coffee.
Hi guys, welcome to the first video I'm putting together for the next topic, which is all about analytical techniques. And so what we're going to be looking at starting today is all about chromatography. Okay, and we're going to be looking at a number of different types of chromatography. We're going to be looking at what we call thin layer. Okay. Sometimes you hear this called TLC, thin layer chromatography. We're going to be looking at column chromatography, and we're going to be looking at gas chromatography. Now, before we go into any of those, you need to understand the basic principles behind chromatography. Okay, so what I'm going to explain is a couple of terms that you really need to get used to, and these are stationary phase and mobile phase. Okay. Now, the stationary phase, as it implies, is a phase that doesn't move. It's something that doesn't move. Okay. The mobile phase is something that moves across the top of the stationary phase. Okay. So if we've got a stationary phase, can be any number of things, and I'll talk about what they can be a little bit later. We've got a mobile phase that sort of sits here, and we pass it across the top of the stationary phase. Okay. Now, generally, we have a difference in polarity between these two. Okay, so one of these phases will be polar and one will be non-polar. Okay, and so what we'll end up with is a stationary phase, and let's say, for example, that we're going to make that polar. Okay, so what we've got up here is a mobile phase, and we're going to make that non-polar. Okay, what we're going to do is bring a couple of molecules in. So this is a non-polar molecule, and this one's a polar molecule. Now what you've got to understand is that all molecules, there exists some attraction between them, normally due to secondary bondings. So it can be hydrogen bonding, it can be dipole-dipole bonding, or dispersion bonding. Just depending on the strength of that bonding and how alike they are, will determine how strongly they're actually attracted to each other. So a common rule is like attracts like. Okay, so if you've got a molecule that's polar, it will be attracted to other things that are polar. If you've got a molecule that's non-polar, it will be attracted to other things that are non-polar. So if we've got our mobile phase here, our solvent that's moving across, okay, which is non-polar, across our stationary phase, which is polar, and we've got our mixture, all right? So we've got this solution which has a mixture of both polar and non-polar molecules in there, okay? As we pass our mobile phase across, okay, what's going to happen is that these polar molecules are going to be more attracted to the polar stationary phase. That means they're going to adsorb to the surface of it. So adsorption is where it really sticks to the surface, okay? And that means it's going to move slowly. So a really good example of this is, take for example a car that's traveling on a road. Okay, it's touching the surface of the road and traveling across it. Okay, whereas you've got something in this case which is non-polar, a non-polar molecule. Because the stationary phase is polar, it's not going to be attracted to it, but it is going to be attracted to this non-polar mobile phase. Okay, that moves across. And so what happens is that as this mobile phase starts to move across, it carries the non-polar molecules with it. The polar molecules travel more slowly, okay, and because they are attracted or adsorbed to the surface of the polar stationary phase. So our mobile phase moves across, taking the non-polar components with it. The polar components sort of stay on the stationary phase and move more slowly. Now the whole process, the reason why we do this is to help separate mixtures. Okay, so remember at the beginning what we had was our non-polar and our polar all dissolved together in our solvent. We made it come through the mobile phase, okay, as it passed over the stationary phase. What happens is the non-polar molecules travel with the non-polar mobile phase. The polar molecules stick or are adsorbed to the polar stationary phase and travel more slowly. That's the principle of chromatography. Okay, it doesn't matter if you're talking about TLC, column chromatography or gas chromatography, they all rely upon a mobile phase and stationary phase and the difference in polarities between them. Okay. So conversely, if we swapped these around, if we had a non-polar stationary phase, okay, and we have a polar mobile phase, what's going to happen this time is that as the mobile phase travels across the stationary phase, polar molecules are going to be strongly attracted to it, so they're going to move quickly. Non-polar molecules are going to more strongly adsorb to the surface of the stationary phase, and they're going to move slowly. So we're going to separate them out again. Alright, so thin layer chromatography, okay, TLC. Okay, this refers to where we normally have just in essence like a two-dimensional plate. Okay, so we're going to do some practicals on this, but we've got a plate. It looks a little bit like this. Okay, and what we've got, you can use paper, but really normally what we're looking at for thin layer chromatography is this has a sort of a aluminium oxide coating across it. All right, it's got a bit of an aluminium backing with an aluminium oxide coating across the top of it. What we normally do for thin layer chromatography is we have a little line down the bottom. This is where we start. Okay, and what we do is I should backtrack for a second. Chromatography is really, really useful because it can tell us two things. It can tell us basically what a substance is made up of. It can help us to identify what they are. Okay, so what I mean by that is it's what's called a qualitative analytical technique. So it can tell us what it is. Okay, it doesn't necessarily tell us how much there is. That's quantitative, but it can tell us what it is. That's qualitative. So what we do is if we've got a couple of different samples, or let's just start with one, for example. Let's just say we've got some black ink, like we've got in this pen, okay, and we spot some of this down the bottom. So we only need very small amounts for chromatography, which is really good. So what happens is that as we apply the mobile phase across the bottom, so this plate, all right, this plate is, I'll get a different colour for this, so the plate is the stationary phase. So I'm just going to shorthand it to stationary phase like that. Okay. What we're going to do is we're going to apply a mobile phase from the bottom. Okay. So the beauty about thin layer chromatography is that solvents travel up the surface of the plate, and what they do is they carry the components with them. Okay. So as this mobile phase heads up the plate, and it's normally just a solvent, okay, it's going to reach a certain point at the top, and that's what we call the solvent front. Okay, so this mobile phase travels up the stationary phase, okay, and what it does is it attracts the component in the black ink with it. So what happens is that you start to see this black ink after a while start to separate out. So you might see, I don't know, a red component, you might see a green component, okay, you might see a blue component, okay. Now all of those, when they're mixed together, give you your black ink, but as the black ink starts to move up the paper, or the aluminium oxide layer, all right, the different inks within it, the different colours, are attracted at different rates to the solvent, okay, to the mobile phase, and depending upon that attraction shows how fast they move. So in this case here, the red dot was very strongly adsorbed to the surface of the stationary phase, so it moved slowly. The green dot was sort of in between, attracted a little bit to the mobile phase, adsorbed a little bit to the stationary phase, so moved intermediate. The blue dot, or the blue component, that was attracted very strongly to the mobile phase, and so it travelled the furthest, okay, and so it had the polarity that was most similar to the mobile phase. So if we decide that in this case our stationary phase of aluminium oxide is polar, and we use a non-polar stationary mobile phase here, that would imply to us that the blue is the most, okay, non-polar, because it's travelled the furthest with the non-polar stationary phase, okay, sorry, non-polar mobile phase, and the red dot here is the most polar, because it's most strongly adsorbed to the surface of the polar stationary phase, or it's travelled the least distance with the non-polar mobile phase. Okay, so that's thin layer chromatography, and all that allows us to do is basically separate out some components. So how do we actually practically use that in the lab? Okay, well, let's say, I'm just going to rub that out, sorry. Let's say that we think we've got a sample which has a particular component in it. Alright, so we've got a beaker over here, okay, which is has been all mixed up, and let's say it's got A and B in it. Okay, what we do, and we want to check to see if they're actually in there. So what we do is we get a thin layer chromatography plate like this. We have our line down the bottom, and we spot our sample. So this is our sample over here. We spot our sample onto it, and then what we also do is spot some of the known A and some of the known B into it. Okay, so we think that our mixture over here has both A and B in it, but we're not sure. Okay, so what we've done is we've taken some pure A and some pure B, we put that on the plate, and we put a dot of our mixture there as well. We apply a solvent. The solvent, or the mobile phase, moves up the stationary phase there, and what we're going to see is that A moves, say, to here, and B moves to there. So they're pure, there's only one thing in it. If our sample does in fact have both A and B in it, what we would see is a dot here and a dot here. Okay, so that would actually tell us that yes, we've got both. Okay, if we didn't see that, if we saw a dot here and here, that would tell us, okay, yes, we've got some B in there and we've got something else. Okay, so it's a way we can kind of determine what is in a solution that could be mixed. Now what I need to introduce you to is something called RF values. Okay, so RF values, okay, are what we call basically retention factor. Okay, and it's a ratio. It's the distance that your sample moved. All right, so the distance the sample moved divided by the distance the solvent moved. Okay, now one of the key things that you should work out from this already is that the solvent always moves the furthest. So we've always got a smaller number divided by a bigger number. So what that means is that our RF values should always be less than 1. Okay, always. If you ever do an RF value and you get a number greater than 1, you've done something wrong on your calculator. So how do we calculate that? Alright, so I'll show you again with a thin layer chromatography plate. So let's just put one over on the side here. Okay, and I'm just going to show just one dot here. Okay, so just one dot here. Here's our solvent front. Okay, and here is where our dot ends up. Okay, so we've got a couple of things here. We've got this here, which is the distance of the solvent. Okay, and we've got this one here, which is our sample. Okay, so let's say the solvent travelled 5 centimetres, and you just measure this with a ruler from line to line. Let's say our sample travelled 3 centimetres. Okay, I'm just doing some nice numbers. So our retention factor, our RF value, is 3 over 5. It's the distance the sample moved divided by the distance the solvent moved. So that gives us a value of, what's that, 0.6. Alright, so our RF value is 0.6. That's how you calculate it. Just measure the distance of your sample over the distance of your solvent. Okay?